in here and then figure out which direction this goes. You know, it looks like it probably goes to the left because the KC is so small. And so it looks like I would put, you know, plus 2x plus x plus, actually not plus, minus minus. Doesn't it look that way? But in this particular case, what we can do is we can calculate QC. QC is just going to tell us, you know, how close we are to K. Maybe it's already at equilibrium, and we don't have to do anything. If it's already at equilibrium, that's nice. So what we'll do is we'll calculate QC. QC is just your given or your initial condition. So if we plug in the QC, it's going to be Fe2 plus squared initial times the Hg2 plus squared initial divided by the Fe3 plus initial squared and then the Hg2 plus initial, just to the first power. And so we plug in all the numbers here. This is going to give me 0.03,000 squared, 0.03,000 squared divided by 0.5,000 squared, and then 0.5,000 here. And so what does that come out to? Okay, I'm sorry, can you repeat that one more time? 6.48 times 10 to the negative 6. Times 10 to the negative 6. Oh, we're very close. Very close to equilibrium, but it's off a little bit. And so when we look at this, initially I predicted it would shift to the left because, you know, this is heavily biased towards the reactants. But does it look like it shifts to the left now? No, it actually shifts to the right because this is a little bit too small. And so we need to take it from 6.48 to 9.14. So going from 6.48 to 9.14 means we need more product. And so the actual direction is this. And so we do it this way. If QC were equal to KC, then we're done. We don't have to do anything because it's already at equilibrium. If QC is greater than KC, which we saw the other day, then it's too top heavy. You know, it has too much product. And so this means the direction of reactions to the left. If QC is less than KC, then it's too bottom heavy. We need more product in the numerator, and so it shifts to the right. And so this tells us the change. We don't know the change should be small because we're kind of close. So the change is going to be minus 2x molar, minus 2x molar, plus 2x molar, plus x molar, or 2x molar. Which one? This one should be just x. And so at equilibrium, what do I expect it to have? At equilibrium, I expect to have this. I'm going to have 0.5,000 minus 2x molar, 0.5,000 minus x molar, 0.03,000 plus 2x molar, and 0.03,000 plus 2x molar. Okay, then what I'm going to do is I'm going to plug that into KC. Here. Try to solve for x. And so Kc is just going to be equal to the iron 2 concentration squared. So that's going to be 0.03,000 plus 2x quantity squared times this squared, 0.03,000 plus 2x quantity squared, divided by 0.5,000 minus 2x. Quantity squared and 0.5,000 minus x to the first. It's too bad that this wasn't squared. You know, if this were squared here, then you know what I could do? Yeah, I could just take the square root of both sides and make the math really easy. Sometimes you get lucky. You know, sometimes this is squared, and then it becomes pretty simple. No quadratic. But this isn't. And so this becomes a fourth order polynomial here. But maybe the change, I mean, we're pretty close to equilibrium. So maybe we could just assume that the change is very small. If we assume that the change is very small compared to the initial, because it's just slightly off, right? 6.48 versus 9.14 times 10 minus 6. You know, slightly off. But what happens if we use a simplifying assumption here? If we use a simplifying assumption here, it fails. The reason it fails is because, you know, the 2x, we assume 2x is small to 0.03 thousand, okay? We assume 2x is small to 0.5 thousand, fine. 2x is small to 0.03 thousand, x is small to 0.5 thousand. If we assume that all the changes are very small, then we can't solve for x because x disappears from the equation. So the SA fails because there's no longer any x to solve for. Does that make sense? Yeah. So what should you do in that case? Well, if we did assume x is negligible, then x disappears from the entire equation, and then we're left, if x disappears from the entire equation, then we're just left with these, the initial conditions, and the initial conditions were, although close, they're still off. And so we can't assume x is negligible. So are there any other tricks that we could do?
Is this where you do the reset?
Yes. We could try resetting it. You know, and if we reset it, maybe that would help us here. Now, looking at the k, which direction should we reset it to? Yeah. So let's go ahead and the math looks kind of complicated. So what we're going to do is instead of this, we're going to just try to reset it. Did anybody reset this? When we reset it, we're going to reset it all the way. That is, we're going to assume, you know, it goes backwards completely. And so in order to reset that, I'm going to have to add plus 2y over here, plus 2y over here, minus 2, actually plus y here, minus 2y here, and minus 2y here. And so we have to figure out what y is. Well, what's the limit? If we go backwards, which one is the limiting reagent? In this case, neither is the limiting reagent, it's stoichiometric, so we have just the right amounts. And so minus 2y must be minus 0.03 thousand molar. That's it. So this is minus 0.03 thousand molar. So 0.03 thousand minus 0.03 thousand gives us our new initial conditions. Our new initial conditions will be here. This will be our reset initial conditions. So let's do green. So I'm going to start off with 0 molar here and 0 molar here. Okay, then over here, if 2y is 0.03 thousand, then y must be 0.01500. So 0.01500 would be altogether, that would give me 0.5150 molar. Is that what you get? Okay, then over here it's just going to be plus 0.03 thousand. So this is going to give me plus 0.0. This is going to be 0.5300 molar. So 0.5000 plus 0.03000 is 0.5300. Okay, so we reset everything to the left. The reason we reset everything to the left is because the KC is small. Okay, then we set up the X table again. Here. Write it over here. Okay, so my reset initial conditions are going to be here, 0.5300. Over here, it's going to be 0.05150, or 0.5150, not 0. Here it's going to be 0 and 0. So there are two reasons to reset. One, so that the simplifying assumption is more likely to work, and two is to get more zeros. The more zeros we have as initial conditions, the fewer binomials we have to multiply out. And so it saves us. Now, we could figure out the direction of change. I mean, if we calculate Q, what is Q here? Q is the initial, so it's the products over the reactants is going to be 0. So 0 is smaller than that, and therefore we expect the forward reaction. So this is going to be minus 2x, minus x, plus 2x, plus 2x. And so at equilibrium, I'm going to have 0.5300 minus 2x, 0.5150 minus x, 2x, and 2x. Now let's plug that into Kc, which is equal to 9.14 times 10 to the minus 6. And so I'm going to get 2x squared, 2x 180 squared divided by 0.5300 minus 2x. And 0.5150 minus x. Okay, the 0.5300 minus 2x needs to be squared here. Okay, so fewer binomials is good. But now let's make the assumption that x is negligible. If we make the assumption that x is negligible, then that simplifies the math a lot. We're just going to assume that 2x is much smaller than 5300. If 2x is smaller, much smaller than 0.5300, then x has got to be a lot smaller than 5150. And so x is going to drop out of both of these on the bottom. And so we use the simplifying assumption, and that's going to make this one, we'll get 2x to the fourth over 0.5300 squared and 0.5150. And so we drop the x out of both of these binomials here, assuming that they're small. And so simplifying assumption, x is much smaller than, or actually we'll do 2x is much smaller than 0.53. Okay, now how's the math? Yeah, the math shouldn't be a problem. We're going to set this equal to 9.14 times 10 to the minus 6 and see what we get here. So just use a calculator on my phone. So 0.53 squared. I'm going to do times 0.515 times 9.14 times 10 to the minus 6 divided by 2 to the 4th power. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So 16, so divided by 16. And then I'm going to take the 4th root of that, so I'll just square root it twice. Square root once, square root twice. And so I calculate an x value equal to 0.01695 for, just carry some extra digits there. Is that what you get? Anybody else get that? Okay, good. All right, now, that means what is 2x? Well, let me just, since this is still my calculator, I'm going to just times it by 2 and see what I get. So 2x is equal to 0.0339098. So what we assumed is this. We assumed that 0.5300 minus 2x is about 0.5300. But when I look at 2x, based on my calculation, 2x is 0.03. So when I look at this, 0.5300 minus 0.03, that comes out to 0.5000, right? Is that really a negligible change? Remember the last problem we did, the change was really negligible. I mean, it didn't really even factor in. In this case, the change is much more significant. Do you see that? And so the change is much more, well, we kind of expected it to be much more significant because this is already close to equilibrium, and then we reset it. And so the change is going to be much more significant than it would have been in this case here. And so how much change is acceptable? Okay, so what we want to do is we're going to validate the simplifying assumption. And in order to validate the simplifying assumption, we have an arbitrary cutoff. The arbitrary cutoff is this. You know, if you're getting more than 5% change, that's pushing it, you know, because a 5% change is significant. If we're getting less than 5% change, we're still pushing it. Let's say it's 4.9% change. That's still kind of shaky. You know, if it were tiny marginal percent change, like we saw in the previous problems, then yeah, no problem. But here, this is an arbitrary cutoff. You know, somebody had to come up with a cut, and that cut is the percent change must be less than 5%. We'll just say less than or equal 5%. Well, maybe if we say equal, then people will round it. We'll come up with a 5.4% change and say that's okay. So it has to be right on. If the percent change is greater than 5%, then not valid. If the percent change is less than 5%, then we'll just say it's valid. It's okay. It's acceptable, the amount of error we're introducing into the calculation. And so let's go ahead and calculate the percent changes for here. So if I look at the first one, it's 0.5300 minus 2x. So for 0.5300 minus 2x, the percent change is just the change over the initial times 100%. Okay, so the change is 2x. We calculate what 2x is. It's 0.0339. We carry some extra. And the initial was 0.5300. And And so what does the percent change come out to for this? And so this is still my calculator, so I'll just divide this by 0.53. This comes out to 6.39% change. Okay, let's take a look. For the other one, the percent change is going to be smaller because it's just x over, 5150. We could go ahead and calculate it. We want the bigger one. So 0.5150 minus x. What does it come out to? So that comes out to 0.016954 over 0.5150, 100%. .2%, 3.29%. And so this one was okay, but this one's not good. You see that? And so it failed. Even though this was okay, this one failed. It fails. Failed validation, unfortunately. So failed validation, does that mean we're out of tricks? We just have to do the algebra? It turns out that we're not out of tricks. Okay, there's one more. There's one more trick that you might already have used in other problems. And so this is the final one, though. One final trick that you can use. And it has a name. It has multiple names. And what it is the method of successive approximations. This is an appendix A in one book. Appendix A. Maybe it's this cable. I can load the book on my computer, but I can't seem to load it on this computer here. I think this cable it's not projecting. But take a look at it and kind of say, this is also called the guess and check method. So what we're going to do is we're going to go back to this one. We could go back to either one. This one just looks a little easier to use for the guess and check. And so we're going to go with KC is equal to 16x to the fourth divided by 0.5300 minus 2x squared. 0.5150 minus x, the first. We know what this should equal. This should equal 9.14 times 10 to the minus 6. That's what it should equal. And so what we're going to do is we're going to guess an x value and then see what k comes out to. And so we'll make a little table here and see how many guesses we can get this to. guess an x, and then calculate k. Well, the first x that we're going to guess is just this one. You know, this was kind of close. I mean, it was 6%. So it was kind of close. But, you know, I don't want to go too many sig figs because that's just a lot of work in the calculator. And so what we'll do is we'll just go with like 0.017. How about that? Maybe 2 digits, make life easier a little bit. And see what we come out with, you know. So we'll try 0.017. So what I'm going to do is I'm just going to use my calculator here. If you have Excel, you know, this would be pretty easy to set up in a spreadsheet. You can do this pretty quickly. But we're going to do this by hand. So 0.017 to the 4th. So I'm just going to square it twice. Twice. Times 16. Okay, divided by, okay, now I'm going to put this in parentheses here. 0.53, parentheses, 0.53 minus 2x. Well, 2 of this is 0.034. So minus 0.034, close parentheses, square this, equals. Okay, then divided by, we're going to do divided by parentheses 0.515 minus 0.017. Oops, screw that one up. 0.017 close parentheses equals. So I get 10.9 times 10 to the minus 6. So the k value of the calculator is 10.90 times 10 to the minus 6. So it's a little bit too big. You see that? A little bit too big. And so I'm going to go a little smaller, I think, because the numerator is to the 4th power, the denominator is to the 3rd power. So I'm going to go a little smaller. But I don't want to add too many digits, so I'm going to go with 0.016. Let's try that. 0.016. Okay, so I'll just do that here. I'll go 0.016 to the 4th. 0.016 squared times 16 equals divided by parentheses 0.53. Oops. 0.53 minus, okay, 2 times that is 0.032. 0.032, close parentheses, square that, equals, divided by parentheses 0.515 minus 0.016. Close parentheses equals 8.47 times 10 to the minus 6. 8.47 times 10 to the minus 6. So it looks like it's between these two. I'm shooting for 9.14. Which one's closer? 9.14 is closer to 17 or 16? Looks like it's closer to 16. And so what do you want to do next then? Something closer to 16. So I'm going to go 16. Four? 4 would be kind of midway. This is 8, this is 11 maybe. 2? 3? 2? That's all right. We'll go with 2 then. Let's try that. Let's see what we end up with here. So I'm going to go 0.0162 to the 4th. 0.0162 squared times 16 equals divided by parentheses 0.53 minus, I'm going to try to do this in my head. This will be 0.324. 0.0324. So minus 0.0324 close parentheses, square that, equals, divided by 0.515, parentheses 0.515 minus 0.0162, close parentheses, equals 8.92. 8.92 times 10 to the minus 6. Maybe the 3's were right. 0.0163. Let's try that. All right. So I'm going to go 0.0163, 0.0163 squared times 16 equals, divided by parentheses 0.53 minus, okay, what's this going to be? 0.0326. That's 0.0326, close parentheses, square that, divided by parentheses 0.515 minus 0.0163, close parentheses, equals 9.154 times 10 to the minus 6. What's it supposed to be? It's supposed to be 9.14. So we're getting pretty close here. So I think I just want to go. It's much closer to 163 than it is 162. So what do you want to do next?
1625.
Well, 25 is going to kind of throw it in the middle. So I would go 0.0162. I'd go closer to 3. It's almost right on 3. 8 or 9 here. What do you think? What do you want to do? 8 or 9? 8? All right, we'll do 8. So 0.01628. See what that comes out to. So I'm going to go with 0.01628 squared times 16 equals, divided by parentheses 0.53. I'm doing this with my calculator here. If you're using the Casio, it's different. Minus 2x. So let's double this. It's going to be 0.03256. 0.03256. 0.03256. Close parentheses, square that, equals, divided by parentheses 0.515 minus 0.01628. Close parentheses. So I get 9.107 times 10 to the minus 6. So this is 11. 911, that's 915. We got to get to 914. So what do you think? Well, let's do 9.5. Let's do 0.01629. I'm going to see where that comes out. Okay, let's do that. 0.01629. 0.01629 to the fourth times 16 equals, divided by parentheses 0.53 minus double this. So I'm going to try to double this in my head. It's going to be 0.03258. 0.03258. Close parentheses, square that, divided by parentheses 0.515 minus 0.01629 equals 9.13. Close, 9.130 times 10 to the minus 6. So we're at 13 here, 15 here. we should go either, it looks like halfway, right? A little bit more than halfway. So we should go with I would go with a 1629, or actually, what are we, 295 or 296? What do you want to do? Yeah, okay, let's go with a 6. So we'll 0.016296. Hopefully that'll get us right there. So we're going to go 0.016296 to the 4th times 16 equals, divided by parentheses 0.53 minus, okay, now I need to double this. So that's going to be 0.032. What is that? Double. 296 would be 592. 592. 0.032592. So what do you guys get? Okay. Minus 0.032592. Close parentheses, square that, divided by parentheses 0.515 minus 0.016296. Oh, okay. 9.144 times 10 to the minus 6. Awfully close. Awfully close. It would be nice to get it to 9.140. That's what I'm shooting for. If I can get it to 9.140, then I'm going to stop. Let me see if we can do it. So what? This is a little bit high. So what are we going to do? 16295 maybe? It's going to be hair under 6 probably. But we'll just try this one just to see where we're at. So 0.016295 squared times 16 equals, divided by parentheses 0.53 minus double this. So 32590. You got it?
Oh, yeah, it's 9.142.
9.142, thank you. 9.142 times 10 to the minus 6. Okay, so we're 4442. We need to go just a little bit smaller than this. So what should we do? All right, we'll try it. 0.016294. Tell me what you guys get. These things are faster. What did you get? 9.140. Give me one more digit. 1 times 10 to the minus 6. Okay. This is close enough. So we're going to go with that.
Is this something that is done often? It seems like the worst way to try to solve for something.
It's done all the time. It's done. They have computer programs that do this. Yeah. And then this is often used because the math becomes horrendous. And once the math becomes so horrendous, then you have computer programs that try to do this for you. This is a very common method, actually, to solve harder math problems.
How do you know where to start with that?
How do you know where to start? That's why we have to use the simplifying assumption. Otherwise, can you imagine just taking a random guess? If you took a random guess, you'd be you don't know where you'd be in the universe, And so if you took a random guess, it's impossible. So this is why we had to use this. This failed for validation, but this was an excellent starting point for this because it was close. And so we started with, I didn't want this many digits because can you imagine punching that in the calculator? It would be too much hassle. So we just did 0.017 as our starting point for X. So if we didn't do this, what would you have picked for your starting point? Just some random guess. If you did some random guess, you might be, 1,000, you might be 1,000 iterations away or 10,000 iterations away from solving it. Which would be pretty bad. How many did it take us? It took us 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 guesses to converge on the answer. So that's pretty good. Some people more, some people less. But that was pretty decent. All right, so now we have an X value. Let's go ahead and calculate the concentrations over here. And so it's going to be 0.5300 minus 2x. And so we need to double this, which was a 0.032598. So right, 0.032598. Is that 47? 94, 40, 44, 88. I got it wrong. 88. And so I'm going to calculate this just in my calculator, minus 0.032588. I got 0.4974. And we'll carry some extra digits here as subscripts. Okay, so this is going to be 0.5150 minus x, 0.016294. Point 498,706 molar. And then this is just going to be 2x. So I'll just go ahead. 16,294. There's the 0.0320. Oh, here it is. 0.032588. And this is the same. Yeah. And so let's double check our answer by calculating K based on these concentrations here. And so I'm going to go with 0.032588. And that's going to be times 16, square that. So I'll go ahead and square that. Well, anyway, do you know the double check what it's going to come out to? Yeah. And this is the same numbers as we just used to calculate over there. And so double checking is going to circulate. Okay, as long as it didn't miscalculate. The thing I could have done is just miscalculated these. So that's another thing, made a simple addition or subtraction error. And So that would be another reason for double checking it. Okay, but you should double check it and see. All right, so that was pretty challenging because we had to use like every trick in the book to try to solve that, right? Okay. Let's check out another problem here. We're going to take a look at number 40. Number 40 says the dinitrogen tetroxide, nitrogen dioxide equilibrium mixture in a flask on the left in the figure is allowed to expand into the evacuated flask on the right. So they have a figure here that's drawn, but I can't show it to you. So I'll just draw it here. There's a valve here. And over here they have 0.971 moles of N2O4. 0.971 moles of N2O4. And 0.0580 moles of NO2. 0.0580 moles of NO2. And the volume for this is 0.750 liters. And the temperature is 25 degrees C, or room temperature. Okay, what they say is that this is at equilibrium. They give us the equation here. The equation is N2O4 gas goes to 2NO2 gas. And so, what kind of reaction is this? This is a redox reaction. Let's see. It's not a redox reaction because the oxidation state doesn't change. Is this a metathesis reaction? Is this a Bronsted acid-base reaction? No, there's no H. Then what is it? It's a Lewis. This is a Lewis acid-base reaction. So we have rearrangements left on us here. Okay, and then they say this is at equilibrium. And they give us a Kc value to this. Let's take a look. That X circle. It just means the valve is closed. So they show it like this. It's closed this way, it's open this way. This is empty over here. Empty, does empty mean filled with air? No, this is a vacuum over here. It's not a perfect vacuum though. It would be 2.25 liters of empty space. I mean, it could be filled with air. It's not a big deal. If it has air, will air interfere with this equilibrium? No. Kc for this is equal to 4.61 times 10 to the minus 3 at 25. 4.61 times 10 to the minus 3, 25 degrees C. So they say that this is already at equilibrium. Let's double check to see. We're going to calculate Q and then compare it to K. So this is going to be the NO2 concentration squared, initial, over the N2O4 concentration, initial. So the NO2 concentration is going to be 0.058 divided by 0.75. That'll give us the molarity. This one here, I for initial. So what is the molarity 0.058 divided by 0.75. 0.07. 0.077333. How many threes do I have? It just keeps going on. Square divided by the N2O4 concentration for the first. So that's going to be 0.971 divided by 0.75. 0.971 divided by 0.75. 1.294. So let's go ahead and calculate this square. On the top is square. Yeah. I should have squared it earlier. I'm just going to do, how many sig figs are we allowed? We're allowed 3 sig figs, is that correct? Yeah. But I'm going to carry one extra, at least here. And so I'm going to go 0.07733. Maybe I'll carry 2 extra. And then square that. Divided by 0.12946. 1.2946. Maybe I'll carry an extra 6 there. I get 4.619 times 10 to the minus 3. Well, if I look at 4.619, that's 4.62 times 10 to the minus 3. Is that really at equilibrium? They don't match. This one's just a little bit higher. Do you see that? But they told us it was at equilibrium. They said that this is at equilibrium. So what do you think the mismatch is due to? Rounding. So it's close enough. This is at equilibrium. So we have this at equilibrium. So there's no change. Now we're going to upset that equilibrium by opening this valve. What happens when you open this valve? Well, the gas can expand into the other container. There we go. Expands there. So I guess we'll go ahead and do that then. So our original initial conditions were this. Our original initial conditions would be 0.0773 over here, 0.07733 molar. And the N2O4 would have been 1.294 molar. I'll just carry one extra digit. We're allowed 3 sig figs. Now, what we're going to do is this initials equal to equilibrium. This is already at equilibrium. And then we're going to perturb it. I'm sorry? 0.07. This one here? This one, it just comes from the 0.0580 divided by 0.750. Just moles per liter. We have to use molarity for these. We can't use moles because we could use moles if it were even, like 2,2 or 1,1. But since it's uneven, we can't. We have to use molarity. If it were even, like 1,1 or 2,2, then the volume would cancel on the top and the bottom, and therefore we could use moles. So we perturb the equilibrium. When we perturb the equilibrium, we're increasing the volume here. So what's going to happen is we're going to have new molarity. The new molarities would be, okay, for N2O4, it's 0.971 moles, but now over 3 liters, the total volume. So this is 0.971 moles per 3.00 liters. It's going to be 3.00 liters because once I open this valve, then it can occupy both flasks. Yeah.
What does that say about the EV?
This one?
Yeah.
Perturb, yeah. Perturb. This is Le Chatelier's principle, so we perturb it. if we increase the volume, which way is it going to shift? To the right. But first we have to figure out why is it going to shift. Well, originally it was at equilibrium. And so now the new molarity of this is going to be 0.971 divided by 3 is 0.3236 molar. And then over here we're going to get 0.0580 moles divided by 3.00 liters total volume. And so I get 0.058 divided by 3 equals 0.0193, so 3 molar. So am I still at equilibrium? And so what I'm going to do is I'm going to calculate QC here. This is the QC for this one. Let's calculate the QC for this one. This one was at equilibrium. This was close enough to KC. We call it equilibrium. Now, when we calculate QC with this one, it's going to equal 0.01933 squared divided by 0.03236. And so 0.01933 squared divided by 0.3236. And that gives me 1.154 times 10 to the minus 3. So when we compare Q to K, is it still at equilibrium? No. Since we increased the volume, it had a different impact on the concentrations here. And what we see here is now we're too big or too small? Too small. So if it's too small, it has to shift which direction? Well, if it's too small, we don't have enough product. If we don't have enough product, we've got to make it bigger. We make it bigger by increasing the amount of product, so it's got to shift to the right. And so this is going to shift to the right. The Q is going to be here minus X molar plus 2X molar. And so at equilibrium, we're going to have 0.3236 minus X molar, 0.01933 plus 2X molar. And so over here, this is going to equal on the top K. Actually, now I'm going to go to K. Solve for K. Let's do that. Get rid of these Q's. So Kc is equal to that, and so we're going to make this equal to 0.01933 plus 2x quantity squared divided by 0.03236 minus x. So we have a couple of choices here. Choice one, we could just go ahead and this is quadratic, so we could go ahead and solve the quadratic and just do the algebra. Or choice two, we could try doing some tricks on this. Now, because if we look at this, which side does this favor? The reactant side or the product side? The reactant side. So what we could try to do is we could try to do a reset and then see if the simplifying assumption works. What do you guys want to do? Do you want to solve the quadratic, or do you want to try doing a reset and see if the simplifying assumption works? You want to try resetting and see if the simplifying assumption works? We out of time? I didn't quite finish this, did I? Okay, let's just do the reset here. Yeah, it's time, so if you have to go, N204 going to 2 NO2s. Okay, then the original initials, we'll plug it in here, 0.03236. And then the NO2 was 0.01933. Okay, we
0.3236, not 0.023.
3236. Okay, now we're going to reset it. And so that means we're going to shift it all to the left. So reset. We're going to lose all of this, 0.01933. How much are we going to lose over here? Or gain, actually. We're not going to lose anything. How much are we going to gain over here? It's going to be half of this. So it's going to be 0.01933 divided by 2. Half of it. And so the new initial conditions are going to be what? So 0.3236 minus 0.01933 divided by 2. 0.31. Oh, I did minus. Shoot, I was supposed to do plus. Let me try that again. 0.01933 divided by 2 plus 0.3236. So I got 0.33326, and this comes out to 0. Okay, then we just plug this in over here to our K. Actually, the change is going to be minus x plus 2x. And so at equilibrium, we're going to have 0.33326 minus x and 2x. And so we're going to get 2x quantity squared because of that divided by 0.33326 minus x. And then we just try the simplifying assumption. So that comes out to 2x quantity squared divided by 0.33326. And that's going to equal 4.61 times 10 to the minus 3. Okay, so I have this in my calculator. I'm just going to multiply it times 4.61 times 10 to the minus 3. Divide by 4. And then take the square root. And so I get x is equal to 0.0195. And then we calculate the percent change. Percent change is 0.0195 divided by the initial 0.33326. So divided by 0.33326 times 100. So close. 5.8%. So close. But it failed. It failed, but it was worth a try. And so what does that mean? That means we have to get this into quadratic form and then solve the quadratic equation. Uh-huh.
So this is the confusion. Is the x on the product and the x on the reactants are different? If we assume, simplifying something, the x on the reactants, how we also have to do the same?
Yeah, we do, but okay, we can't say this is 0 plus 2x.
Yeah.
So this is 0 plus 2x. Can we assume that 2x is small compared to 0?
Oh, no.
No, so we can't assume, because anything's big compared to 0.
Okay.
So we can't do that. Okay, I'm going to hold some homework sessions probably via Zoom. I'll post an announcement of those.